Welcome everybody who has joined already. Today we have research seminar with Saeed Rahimpour. I hope I pronounced it right. You can correct me if I'm wrong. And for welcoming words, I would give word to Sanya. So please.
Thank you, Crystal. Thank you, Said, for accepting our invitation to give this talk. Even though there is not a lot of people now here, I am pretty sure that people will watch this recording afterwards because the topic is more than interesting and important. It is about enhancing resilience in power electronics, securing the future of energy conversion. I think that the topic is extremely important nowadays when we are suffering the crisis in energy supply, and there is a lot of possibilities for further exploring in this area. So I can foresee a bright future for Said around his topic and his expertise. So Said, if you agree, I can give floor now to you and you can proceed with your, there is no doubt, interesting and engaging presentation.
Thank you so much, Sanya. So let's start. Welcome everybody to my research seminar, of my Siberia. And the title of this seminar is Enhancing Resilience in Power Electronics, Securing the Future of Energy Conversion. Let's start with the basics of power electronics and why power conversion is such a big deal. Imagine all the different devices we use daily and the variety of ways we generate the power. You can see the green sides, the green sources of power on the left side, like solar panels, wind turbines, and traditional power plants. And on the right side, you can see the devices where we need the power. Between these two parts, generation and consumption, there are power conversion units. And power conversion is the process that makes sure these devices and these sources can deliver energy in the best form that is useful to us. Like the devices that handle this are called power electronics converter. And power electronic converters are the backbone of how energy moves from the source to whatever it's needed, to our loads in our houses, in the industry, in the manufacturers. So in simple terms, power electronics is all about controlling and converting the power efficiently. It's split into 4 key parts. Production, which means generating the energy, generating the power we need. Distribution, getting it where it needs to go to the loads, to where we need the power. Consumption, how devices use it. And finally, control. That is about making sure everything runs well and smoothly. And here is where it gets interesting. Different sources like solar panels or wind turbines, they don't always produce consistent power. So power converters have to talk to each other and to keep things balanced. If one converter is working too hard and gets overloaded, others can pick up the slack and making the whole system more reliable. And without control, the components in the converters, they can fail because of wear out, and they can wear out faster, and the lifespan of the equipment is cut down. Therefore, smart control strategies help spread the load and keep everything running efficiently. Let's talk about cyber physical systems. Every day we know that, and we see that systems are becoming more digitalized and they're getting smarter and more responsive. And we can say that they are increasingly integrating more and more into cyber-physical framework, which is essential for modern industries like energy, transportation, transportation including maritime ships, and also manufacturing. So yes, with this framework, with this cyber-physical framework, they gain flexibility, but also they become more and more vulnerable to cyber threats. So increasing the resilience of these systems is of great importance. Let's talk about the resilience part. Resilience is the system's ability to adapt, recover, and continue to work even after faults. And it can adapt to unexpected issues and recover quickly when something happens in critical applications such as transport, healthcare, and other applications such as maritime or industrial automation. And it protects against cyber attacks, and not only cyber attacks, also hardware failures because of any kind of faults, and also natural events. So resilience is about that. Let's discuss cyber threats in the maritime sector. Over the recent years, cyber attacks on the maritime sector have sharply increased, and the main reason is shifting toward greater digitalization, as I said. And when it's smarter and more digitalized and more and when there is more reliance on interconnected systems, therefore the system will be vulnerable to attacks. Another problem is the industry's complex structure and outdated protocols make it also more vulnerable to cyber threats. Average incident costs of cyber attacks to the ship has been $3.2 million over the past few years. So there are significant financial impacts. Also, maritime companies are responding to these cyber attacks, and they try to address it by their new methods and also continuous monitoring solutions. And companies like, for example, Saeed, Everlight, they can try to detect and mitigate these cyber attacks. So as cyber threats continue to grow, the maritime industry must prioritize proactive security measures and real-time monitoring. So we talked about power electronics, we talked about cyber threats to the ships. Let's see where is this power electronics in the ships and maritime sector. You can see a ship, and we can say that power electronic systems in ships play an essential role in energy conversion, distribution, and control. In the ship, you can see the propulsion system. These are increasingly electric over the past few years and making them more reliant on power electronic equipment. And here, power electronic converters controls in the propulsion system. It controls the flow of electricity from the power source. Here, it's diesel engine, as you see, to the electric motors that drive the propeller. They convert and regulate the electrical power for precise control over motor speed and direction. This lets operators adjust the ship's speed smoothly and efficiently. And it reduces fuel consumption and also CO2 emissions. So this is the importance of using power electronic equipment in the propulsion system of the ships. That is, it can increase the efficiency and reduce the emissions and fuel consumption. Also, in the power distribution part, in hybrid electric or fully electric ships, There are controlled power electronic converters. And also in navigation and communication system, they are also supported by complex electronic networks right now. So you remember I talked about the cyber physical systems, and now we're talking about cyber physical systems in power electronics. Power electronics has evolved from simple centralized control systems, and they're becoming more complex with distributed architectures getting more digitalized with embedded cyber physical elements. But as I said before, digitalization brings new challenges, and this figure helps illustrate them. This person, we can think of it as a power electronics system. Think of the physical system as the body of this human and the cyber layer as the brain. If someone comprises any of the units in the cyber layer, they can manipulate the system's data, the whole system's data. So it's the brain. This leads to false control commands that affect the entire operation. And each of the blocks in the body of this person represents a power electronic unit, all communicating with each other by that brain. And these units provide control, frequency control, voltage regulation, reactive power management, and they stabilize grid frequency. And active power needs to be dispatched so we can use the cyber layer. However, this interconnected communication makes the system more vulnerable to cyber attacks, and they often target this area, the cyber layer. Because for the physical layer, of course, they need the physical access. And in power electronic, faults and anomalies happen very quickly and sometimes within just 1 or 2 milliseconds. And this makes it more difficult to distinguish between a fault or a cyber attack in real time. To tackle this problem, we need improved and better visualization, advanced monitoring and diagnostic tools and control facilities. You can see the components of cyber physical systems. So there is physical layer, including devices, sensors, and converters. There is cyber layer, including the communication networks and energy management. And there is cyber physical layer, which is includes control algorithms and also the sensors. Let's talk about the physical layer. The physical layer, it's obvious, it includes all the tangible physical components that we can access physically, like motors, generators, transformers, converters, sensors, and other hardware in the production, distribution, or consumption of the energy. What does it do? It performs the actual electrical and mechanical operations and the power flow. And it is influenced by the commands from the higher layers. What are the higher layers? Cyber layer and cyber physical layer. There are challenges with inside the physical layer, steel. And those challenges are component level and system level reliability and the wear out failure. So as I said, the physical layer is not vulnerable to cyber threats a lot, but it has its own challenges. So here we can see physical layers reliability, and we can discuss the reliability of the physical layer from two aspects. On the left side, we can see fault management. So it's about component level and system level reliability. Here we need to diagnose the fault in the first step with the model-based or data-driven techniques. Then we have to isolate or clear the fault. And finally, we should compensate or reconfigure the system to handle the fault with hardware redundancy technique or switching asset redundancy or unbalanced control techniques. On the right side, as I mentioned, there is another challenge for physical layer, and that's wear out, aging of the system actually. So in the lifetime management part, we are dealing with lifetime analysis. It means that we should first analyze the failure modes, failure mechanisms, causes, indicators, and failure data. And then we predict the lifetime, assess the lifetime with component level or system level approaches. And finally, for extending the lifetime, we are going for reliable design methods and also condition monitoring, where when everything is done, we need condition monitoring. About the lifetime estimation or assessment that I mentioned, there are handbook-based approaches which use historical data from reliability handbooks. There are model-driven approaches. They rely on mathematical models based on physical principles and failure mechanisms of the components. They give a very accurate lifetime prediction, more accurate than lifetime handbook-based approaches. There are data-driven approaches. These techniques use statistical and AI-based models trained on operational data to predict the remaining useful lifetime of the converters. And also there are hybrid lifetime prediction methods that combine all these 2 or 3 of these methods to perform a lifetime prediction. Let's talk about the other layer of the power electronic systems, the cyber physical layer. Or we can call it primary controller. Cyber physical layer, it includes either microcontroller or digital signal processor, and it directly interacts with the physical components. So it's also very close to the physical components actually in the system. The primary controller performs local real-time tasks like voltage and current regulation, as well as PWM control, and it ensures that the converter operates efficiently and maintains stability, especially in dynamic environment like ships that experience rapid changes in load demand. So, voltage and current regulation, motor control for propulsion, and power quality management are the tasks of this layer. From the cybersecurity aspects, since this primary controller operates independently and with the physical part, and it's often local, hardware-based controls, it's less vulnerable to cyber attacks compared to secondary controller that I'm going to talk about. Most cyber attacks to this part would require physical access to the converter hardware, which is usually secure on a ship. While microcontrollers are not completely physically isolated when connected to communication modules, they're not physically isolated, but they're functionally isolated in the primary control tasks, and they're not directly exposed to the network. Because of the function, they're isolated. Let's talk about the most important layer that is vulnerable to cyber attacks, cyber layer, or we call it secondary controller. This controller includes programmable logic controllers, or we call it PLCs, industrial computers, or distributed control systems, or SCADA, supervisory control and data acquisition. It coordinates multiple converters and manages overall power distribution, load balancing and fault tolerance, digital communication networks, and data processing units. So the function is load sharing and balancing, digital communication of the networks, power management, and fault management and isolation. So, as I said, it is essentially the brain of the system, and it enables the decision-making and control over the physical layer. From the cybersecurity aspect, since secondary controller may use networked communication, for example, for remote monitoring, diagnostic, coordination with other ships also, or inside it itself, it is more exposed to cyber threats. So this part is the most important part. For example, an attacker can exploit this communication to interfere with the propulsion to inject false data. It is located in the ship's power management system or central control room. So the cyber physical part was inside the physical part. It was close to the physical part, but this one is in the central control room and where they can monitor and coordinate the entire electrical system. And there is cybersecurity layer. We need this layer to tackle and address the cyber attacks. This layer includes cybersecurity functions to protect the data integrity and network communications. And this layer ensures that the data received by the secondary controller is valid and prevents unauthorized access and preventing the control system from cyber attacks. Let's talk about the types of cyber attacks. First one, there's 3 types of cyber attacks. In general, the first one is false data injection. It injects false data into the system, such as changing sensor readings. So sensor reads some values, but it alters them so that controllers receive incorrect information. So it leads to wrong decisions, and or maybe it can damage the system, disrupts some functions and performance. The second one is man-in-the-middle attack. An attacker intercepts and modifies the communication between controllers. It alters the values such as voltage, for example. So it interferes between the controllers. So as I said, each controller, we can say they're each controller is not vulnerable to cyber attack, but when they are connected, they are more vulnerable to cyber attacks because of their communication. So it can lead to incorrect operations as the system acts on manipulated data and wrong data, and it can cause instability or even failure. The third cyber attack is denial of service, or DOS. It blocks or disrupts the data flow to prevent controllers from communicating to each other. It causes a complete breakdown in communication between the controllers that they have attacked by denial of service, and it affects the system's ability to function and leads to shutdown or interruptions. So how do cyber attacks on ships happen? There are some ways that they can attack ships. For example, from Internet of Things and cloud integration. Attackers may target sensors, tracking systems, and diagnostic that rely on internet or cloud access. And or maybe through the exposed network ports like APIs or weak passwords to exploit vulnerabilities in the cloud provider system. The second one, increased connectivity. Attackers can intercept or hijack communication links by satellite communication and onboard Wi-Fi networks. Now, all the ships, especially the ones that are not military, they have Wi-Fi, they have internet, they have satellite connection. So the attackers can exploit it, and they can use, for example, man-in-the-middle attacks on exposed networks, often via Ethernet, satellite signals, or Wi-Fi. Also, the third one, attackers may exploit vulnerabilities in the networked systems that correct navigation, propulsion, and communication. they can inject malware. They can install malware in the system, and they can damage the navigation, propulsion, and communication. Also, remote maintenance can be also a bottleneck for ships because cyber criminals can exploit remote access tools that they are remote access for software updates and diagnostics, and they can target remote management interfaces, update mechanisms, and diagnostic tools. Finally, it's interesting that they can also exploit human factors. For example, with phishing emails or impersonation attacks of the crew members of the ships or shipping company staff, they can gain access to onboard networks. And it's very common, actually. So maybe it's better to train crew members more. And the sixth one is the more interesting one, actually. There are some sophisticated attacks that, for example, they can compromise systems during manufacturing or distribution. They can put the malware as in the back doors of the system. So the smart attacks initiates, but you can see normal operation. It remains still for months. So for example, on New Year's Eve, it starts to work. It starts to damage the system and disorient the system operation later. So it's the worst, actually, cyber attack. And so maybe more research should be done on detecting these kind of malware in the system before anything happens and before it's too late. So you remember I talked about the layers: physical layer, it's hardware only; cyber physical layer, it's primary controller for local control; cyber layer, it's secondary controller for system-wide coordination; and cybersecurity layer for protecting the communication and data integrity. For example, this cybersecurity detection method is control with the control theory based. You can see it's include the primary controller, secondary controller, and cybersecurity layer. This primary controller, or as we can call it, cyber physical layer, it manages the local voltage and current regulation here. The secondary controller or cyber layer here, it observes the voltage for stability. It regulates the current. You can see there is current regulator, a voltage observer. And the cybersecurity layer works in this way. It verifies data among units, and if data fails, it activates single reconciliation. It labels the faulted and suspicious signals as false and the other signals as true. And then it replaces the faulted ones with some reconstructed signals based on what we expected. So it can buy time for the maintenance. So let's talk about the other methods. There is also, along with the control theory method, there is observer-based approach, which uses the model of the system and real-time data from sensors to estimate what's happening inside the system. It relies heavily on having an accurate model of the system. And it can be slower because it continuously estimates states rather than reacting directly on events. So the problem of this one is being slow. There are machine learning techniques and deep learning techniques, and they analyze large amount of data to learn patterns. And once they are trained, they are quick. They quickly recognize faults or abnormal situations. And but the problem is that data needs to be learned and to improve the accuracy. So they rely on the mathematical models of the system. Also, sometimes reliance on some faulted data may also be a cyber attack. Anomaly detection, another approach. They watch for unusual behavior that doesn't match the normal behavior, and they signal a potential issue. So it directly looks for odd behavior and just go for it. There is also event-triggered control. It waits for the specific conditions and it focuses on big changes or event. It allows for a fast response. So for example, in circuit breakers, when there is a short circuit fault in the system, the circuit breaker acts very fast and it's event triggered. It focuses on just one event. What is that one event? For example, we say to the system that when the threshold, we set the threshold for the current, for example, 50 amps. When it exceeds this threshold, it will just trigger the control and prevent the damage and cyber attack. But the problem of this one is that it overlooks gradual or subtle changes. So sometimes the change is gradual and is not that fast. So it may trigger wrong. There is also intrusion detection. It monitors the network activity for unusual behavior, and it's good at catching network-based threats. And finally, the method that I talked about, control theory-based detection. So it uses the system's natural behavior and dynamics to detect these cyber attacks. So something is good about it. So the researchers try to use it more, actually, also, especially in the papers, because it just needs the dynamics of the system without relying on extra sensors and models. And it focuses on real-time responses based on how the system should operate. Unlike other methods that depend on additional data and models, this approach directly leverages the system's intended behavior. And it allows for fast detection without needing historical data. And because also companies, they don't want to give very special data of their system. So that's one of the problems when some machine learning systems or other techniques want to handle the cyber attacks in some companies, but the companies, they don't want to give more information about their system. But with this approach, just knowing the dynamics is enough and natural behavior of it. This is cybersecurity framework to tackle the cyber attacks and prevent them in power electronic systems. So, the requirement for cybersecurity solutions in power electronic is that they must be extremely fast, accurate, and precise. For these systems, fast means within a few milliseconds. Any delay beyond this can result in overvoltage or trigger current relays or cause system shutdown, all to possible cyber attack rather than an actual fault. You can see the one that I highlighted. This is the traditional framework. This focuses on anomaly detection. It differentiates faults like sensor or grid faults and applies the protective measures to restore normalcy. So it just differentiates the sensor and grid faults. But now we need an additional stage, which is essential: cyber attack detection, followed by immediate mitigation in some milliseconds. The entire process from detection to mitigation must occur in mostly in some standards says that it should be less than 5 milliseconds to prevent damage and maintain the system stability. So first it should detect it, then it should mitigate it, then normal operation. So you can see the loop. So on the right side, it was the traditional framework. On the left side, or we can say the whole system is the modern framework. We can see more technical framework. On the upper side, we can see the data-driven approach. So basically, we have two ways to detect if something is wrong. So I talked about many approaches for detecting these cyber attacks, but mainly, in general, we have two approaches. It's either data-driven or model-based. So one way is data-driven. We save years of data to the cloud, then train a model to recognize the normal patterns and flag anything odd and strange that happens in the system. But here's the catch. If someone messes with that cloud data, it could lead to false alarms or missed attacks. So each approach, it has strengths and weaknesses. And you can see the model-based approach. The good thing about model-based approach is that there is no data sets in this one that someone can mess up with the data set and give the wrong data. So maybe it's more safe. But now in research, they're trying for hybrid methods. They combine both methods, so they can gain the strengths and weaknesses of each one, strengths of each one, and make a more powerful and tough to fool detection system to keep the systems more secure. So these are some references that I used in my presentation. Over the recent years, there are lots of research on cybersecurity of power electronics. As I said, power electronics is emerging in all applications, and in ships even more emerging, and therefore cybersecurity is very important in a maritime sector. Thank you so much for your attention.
Thank you so much, Saeed. This was really impressive work in terms of how actual it is and how you put it in a very short time in the context of cybersecurity needs in maritime. And I will open the floor for question, comments. So please free to raise your hand and ask if you have questions. Okay, I can see a lot of applauses. So Saeed, okay, Ahmed has a question. Please, Ahmed, go ahead.
Can you hear me?
Yes,
Yes.
you can.
Yeah.
Yes.
Thank you for the very interesting presentation. I really liked it. I have a question regarding the machine learning approach in terms of the detection, threat detection. The question is, in maritime domain, is there a lot of, I would say, data sets about logs that happen to monitor or log or catch attacks that can be used to train the models? And if not, are you or part of the team are working on generating such logs? Thank you.
Excuse me, could you rephrase it and say it again? Because
Okay, I will make it shorter. So, in terms of training the machine learning models to help with threat detection, do
yes.
you have the source data set for that already some examples of a detection in maritime regarding cyber attacks?
No, actually, I don't have any data sets right now. So yeah, at the first step, I'm seeking actually the control theory-based method, which is now in research and also in industry is more popular, the control theory, but also machine learning is very interesting, and that one is also used in some research. And as I said, we can do it hybrid, actually, use both data-driven method and with machine learning and also the control theory. But right now, I'm seeking the control theory-based technique. So no, I don't have any data sets right now.
Oh, thank you very much.
I can add upon this question and answer. So as far as I know, the cyber attacks were recorded on navigational systems and positional systems on board ship. There is not much recorded attacks on propulsion system, and it's very difficult to expect of us to have such a kind of data already, but it doesn't mean that such attacks cannot be simulated, and maybe we can start from simulated attacks and do experiments, and in that way act proactively in terms of developing algorithms for identifying early detection of risk and undertaking quickly mitigation actions.
Yes, exactly. Thank you for completing the answer. Yes, as I said in my presentation, the propulsion system, the power electronic of the propulsion system is not that vulnerable to the cyber attack. And you said that the data sets is hard to get, but actually there are connections with the controllers in the network base, and that one can be that one is more vulnerable to cyber attacks, and maybe we can seek to work on that area actually.
Yes, I think we should put effort in creating simulation models or test beds on which we can do experiments and see what is happening, what can happen, and act afterwards. Yes, Shaima, please go ahead.
Yeah, thanks, Said, for this nice presentation. And actually, I have a minor question. It is mostly about the architecture model that you presented, because I am used to the Purdue one, the PERA, and it's my first time to see this cyber physical. So I just wanted to know if it has a name, or this is something that you are introducing, or what.
Which has AIM?
I'm talking about the architecture model of cyber physical system that you presented, this layers of cyber physical, like
Yes.
the physical. Yeah, I am used to the PERA one, the Purdue, which is the field layer, the 5 layers of Purdue. So I was asking if the model you presented has a name, this one you presented today.
The model has a name. No, it's just the power electronic system that has 4 layers, and I introduced it to know that which part is vulnerable, which part is not, and what do we have for each part. For example, because we should know the layers. There are 4 layers,
Yes.
and we should know that which one we should work on. For example, for the physical layer, there are attacks on the physical layer, but they're mostly physical, with physical access.
Yes.
But for example, Yeah.
Sorry for interfering. I understand this because I'm teaching this. I was asking because I'm teaching the para model, and I was asking if there exists some other known models similar to the one you presented today. Because even in the IoT there is the 3-layer model, the 4-layer model, the 5-layer model. There are different architecture models. So my question was, the model you presented today for the architecture, does it has a name like?
I get it. Yes, I get it. No, it doesn't have a name, but
Okay.
but in some papers, you can see that in some research, they just talking about 2 layers, for example. They say that there is physical layer, there is cyber layer, and they put the cyber physical layer, for example, in some research in the physical layer, in some research, they put it in the cyber layer. So I think this is more precise. This is a precise model. So we can say it's 4 layers, but in some research, they say it's 2 layer. It's not that much a difference, actually. I think.
Okay, I got it. Thank you so much. And I have actually another question, because yesterday we had a session in my course about the maritime cybersecurity again, and we were discussing this kind of challenges for even if the system, if we have IDS system on ship, it's like even if there's an alarm, most probably no one will be taking care of that alarm, because actually most of the time there are no cybersecurity professional there. So I would like to know your perspective about what do you see, how we may integrate such technology that we are working in the future. You think that there should be some kind of SOC on ship, or maybe centralized SOC, that the ship would be sending alarms to some SOC, or how do you see it? Because I understood that this is currently not in place. So even if an alarm came on board, most of the time it won't be there won't be someone to take care of that alarm.
Yes. Thank you so much for the question. So we can say that there are different methods for this. In some cases, when cyber attacks happens, yes, there is an alarm, and you should go for it. You should go for the maintenance. You should go for the address it yourself physically. But now in research, we're talking about the autonomous and automatic way of tackling the cybersecurity attacks. So without just sending alarms, that we should physically go and prevent it and tackle it. So it should be autonomous. Of course, on the ships, there may be, in most ships, there may not be the members that know cybersecurity, but the challenge is that we should make as much as we can the ships resilient. Okay, so we try to make the ships more resilient to cyber attacks, but of course, this is undeniable that there will be in some cases, and there are now some companies that do this actually for shipment companies. So there are many companies right now. There are many websites you can pay. You can have a contract to monitor continuously all the facilities on the ships to prevent the cyber attacks. So, and I said in one of my slides that also the crew members must be trained. Actually, at least they should be trained to not allowing the phishing emails and cyber attacks through the internet and unauthorized accesses to the crew members' credentials. So Yeah.
Thank you.
So
Thanks
we
a
should
lot.
consider all the factors. So, and we can't always have all the factors that the crew members they know cybersecurity, and so it's undeniable that we improve, cyber criminals also improve. So we should be one step ahead of them. Yeah.
Thanks a lot.
I would like to end on this, that DNV, which is one of the leading classification societies, has been working seriously on preventing cyber attacks on board. And the requirements for the new ships, of course, will be more strict. So it is a holistic approach. So private companies, academia, and companies, and also shipping companies and classification societies, they are all involved in preventing such a kind of attacks, and it is very demanding task, and we are all trying to contribute in our capacity to a certain extent. And regarding the layers question, I agree with Saeed that in different literature sources you can find a different number of layers, and they are different arrangements. So when I was learning about that a long time ago, it was 7 layers, then they are reduced to 4 layers. And as Saeed said, sometimes they are reduced at even 2 layers. And we should be aware that layers are a high level of abstraction of what is happening in reality in their real devices. And we should just use them as approximation of the very complex real systems, subsystems, and so on and so forth. So there is not, how to say, strict diversification among these network layers that we are talking about here. Just a small, maybe, comment upon the question and answer. Yes, Pentti, please, you can go on.
Hello, everybody. You can hear me? Thank you,
Hello.
Saeed. It was very interesting. I'm not expert in this area, but I learned a lot. Thank you. Maybe one question about your opinion. As you know, with Ahmed and many others in TalTech, we are discussing about the Security Operations Center. So how you can see that? Is it good idea for Maritime?
Excuse me.
I mean, security operation centers are now discussed that they can help in preventing cyber attacks. So have you seen any papers on that topic? Can security operation centers be a good idea to decrease the risk?
You mean having security?
As a center to monitor, the idea is that they monitor the maritime traffic and they monitor networking, and they monitor somehow. It's the same as you said, the consulting companies, but I mean, security operation center is one way to do it, as far as I understand. I mean, I just want to know your opinion about. Just wanted to know your opinion about it. Have you any experience or any papers on that topic?
Yes, there are some general information about this actually in the papers, but not actually very technical one about it. So maybe I will look for it and give you more information.
Maybe Ahmed can comment. Ahmed is our expert in my group.
Yeah, perfect.
Yes, Ahmed, please go on.
Hello, thank you. So just I wanted to add the Maritime SOC, or Maritime Security Operations Center. It's a new and I would say an interesting approach in terms of increasing the cybersecurity of vessels. The problem of application of SOC is the data transmission from the ship itself to the onshore facility, which will be responsible on the data or the logs processing, and if so, doing something about it, like some after the fact or after the incident response. The problem that we are facing now is as you explained today, we have a lot of electronics and we have a lot of devices within the ship itself, and not necessarily controlled or connected together, and even not all of them on the same level of cybersecurity. So this is one approach to think about it. And now, since we are moving into more autonomous ships, it's even more crucial to have something to monitor all the activities within the ship itself. And the SOC is a very well-rounded solution for that, because it is very adaptable and can be very dynamic in terms of increasing or adding more technologies to it. So I would say there's a few papers about it, because this is a very new thing, and I've been working on that for some time now. And I would say the applicability, it can be done, but it's still facing some technical horrendousness. But yeah, but I would say it's quite a good solution, at least from my side.
Thank you so
Thank
much
you.
for your valuable comment. Yeah, thank you.
Thank you, Ahmed.
Thank you.
Aybars, please go ahead.
I would like to add something regarding the security operations centers, if possible. Currently, I'm working on the Maritime Cybersecurity Operations Center. This is my next paper, probably, and we will be together with Professor Sanya Bok and professors from the Singapore University of Technology and Design for this paper. Security operations centers are divided into two groups currently, as far as I know, one of them for companies, one of them for governmental organizations. The first governmental organization, as far as I know, was founded in Singapore in 2017, as far as I recall. It was a small group, 1, 2, 3, 4, 5, 6, probably around 10 operation experts, and also there were some management experts for this center. And the data, yes, somehow can be received from the vessels, at least for the AAS, for instance, because some governmental organizations already provide this data free of charge through an IP address and port number. For example, Norwegian Coast Guard or Norwegian Maritime Authority, as far as I recall. And this operation center also can detect any potential GNSS anomalies, such as GPS jamming, GPS spoofing, or other GNSS variations, such as GLONASS, BIDO, and others. If you consider about the company cybersecurity operations center, it will be different, because in that case you can receive some network data, and several companies, currently these are cruise ships, have dedicated maritime cybersecurity operations team, and this team has a security operations center. Of course, we can discuss it is negotiable to their capability. However, somehow it is possible.
Yes, thank you so much for the comment.
Yeah, I think that they made the first SOC in USA in 2014. Then the second one was in 2017, as Aybars said, in Singapore. But there is not a lot research papers about that. And yeah, I think that Aybars mentioned to me recently that in Denmark they have some attempts to do it, and it is possible, of course, but yeah, it needs further research. And sometimes it might be challenging in the scarcity of reliable resources. But that's our job. Thank you very much for your insightful comments. Do we have maybe more questions, comments? I have to say that it's impressive that Saeed for a short time tried to figure out how it works on board the ship. And yeah, it's a good start for us to think out about new ways of connecting and reconnecting and do further research together. So I think this is a good starting point for us to maybe decide how to go further and do deeper research in this field, which is really a challenging one.
Yes, as you said, it's been about 1 month and a half, I think, that I've dived into this area from the beginning, cybersecurity of power electronics. So I would be really happy to cooperate with other colleagues regarding this, in papers, in research, in their projects, everything. So please don't hesitate to contact me, and I will not also hesitate to contact you. I will, especially to Ahmed Ibers, I will talk to you about regarding this work. Yes.
Excellent. Excellent. So if you don't have more questions, I will close this session, and thank you very much all for your time, and especially Saeed for his effort put into the presentation and for his nice talk. Thank you very much.
Thank you so much, everybody.
Thank you.
Thank you.
Have a
Bye.
great day.
Have a nice
Bye.
day.
Have a nice
Thank you.
day.
Bye.
Thank you.